Okay, so here you are, Bob.
Great. Thanks, guys. You know, there are a few of us. If you want to move up, you're welcome to move up. If you want to stay where you are, I know about inertia, so that works good, as well. I wanted to talk today about just small package CHP, combined heat and power. Who doesn't know what combined heat and power is in this room? No hands. That means everyone knows. Okay, so that's simple. What we're doing is we're producing electricity and usable heat from one fuel source. In this case, we're employing a natural gas fired V8 engine, and here we are. It's made by Tecogen, which is a company that's based in Waltham. I'm using this as a specific example because that's the type of technology that I'm familiar with. If you have any questions during the course of the presentation, I just encourage you, we're just a few here. It's not a big deal. Raise your hand, shout it out. Where's my heckler? I didn't see him here. It's a V8 engine. They're quiet. They only turn 1825 RPM. They occupy the space of about a sheet of plywood, and they recover heat with water temperatures as high as 230 degrees to the tune of about 500,000 BTUs an hour while they're producing 75 kW of power. There's also an alternate unit that's an inverter-based technology that can produce 100 kW of power or sprint up to 125 kW. And because it's inverter-based, is able to stand alone and provide standby power or convenience power to a site when the grid goes down. The induction units are grid dependent, so when the grid goes down, the unit goes down until the grid comes back up. It's a very simplified electrical connections. They produce low emissions because they have catalytic converters that are built onto them that meet the Southern California air quality standards, which we know are the strictest standards in the U.S. I mentioned the simplicity of the interconnection. They are microprocessor-based, typically either internet or telephone. Here's my heckler, or telephony based, so that we can communicate with the systems remotely. If there are any hiccups, the maintenance team knows about it, is able to diagnose it, remotely monitor and modify it, or if necessary, send somebody out to take care of them. The systems, because they're so efficient, also offset carbon, and that's why they can be classified as green technology. Although they're not, and it's really the combined heat and power lobby's bad that we've never been classified as a green technology because we consume natural gas, whereas fuel cells somehow are classified as green even though they consume natural gas as well. But here's an example of a system that, if it's running 7,000 hours a year, is able to offset almost 300 tons of carbon, which is the equivalent of the carbon absorbed by over 80 acres of forest or taking more than 50 cars off the road. Again, the benefit is that not only does it save money, but it save carbon, but it saves money as well. And the reason is because the value of the energy produced exceeds the cost of the value of the energy that is needed to make that the result. So typically, and I'm going to use an example that you'll see later on, a 150 kW system operating 7,000 hours a year can reduce energy costs by about $100,000 or more, depending on what you're paying for electricity and heat today. This chart you have to read from right to left, and what we're looking at as an example is a facility that consumes 75 kW of power an hour and 490,000 BTUs of energy. If it were produced with if the heat were produced with a conventional boiler plant that's 75% efficient, and we look at the 33% efficiency of a central power plant, it would require 121 units of energy from a natural gas well to provide the annual amount of energy that's required at this facility. If you employ a 75 kW system, that amount of energy required drops from 121 to 65 units. And this essentially demonstrates the effectivity of combined heat and power versus a conventional heating system and being attacked to the grid. So here you're saving about 65,000 therms of energy a year. A typical schematic is a V8 engine that's yoked to a generator. As the natural gas is burned in the engine, the generator spins and produces electricity, which offsets electricity that otherwise would have come in from the grid. The heat that's produced during the ignition process of the engine is captured to the greatest extent possible through a multiplicity of heat exchangers, so that the exhaust gas that goes up the stack really only represents about 15% of the energy that's consumed. All the rest of the energy is converted into either A, electrical, or B, thermal energy. And as I said, the hot water that's produced can be as hot as 230 degrees. Typically, the hot water can be used in industrial applications for commercial laundries, plating baths, food processing plants, preheating condensate return for steam boilers, or to make domestic hot water and to heat building space in residential, hotels, or nursing homes, or et cetera. It can also be used to heat swimming pools and spas, and through an absorption chilling process, the hot water actually can be converted to chilled water, which is a bit of a mind bender, to produce chilled water for air conditioning as well. The rule about CHP is this. It's very basic. Run hours, run hours, run hours. You have to run a preponderant amount of the time, and during the time that you're running, you have to be able to utilize both the electricity and the thermal energy. So it's not cost effective to sell the energy back to the utility. Some people think, well, I got this little box that makes electricity. I can just sell the energy back to the utility. I'll make a bundle of money. Wrong. It's because it's not cost effective. The utility will only buy back the energy at avoided cost. And if you plug that number in to what you're paying to run your cogenerator, it doesn't come out in the positive. So run hours is the name of the game. A benefit, a side benefit, of course, is the environmental benefit, where you're offsetting either gallons of oil, or it can be quantified in tons of carbon, or numbers of car or acres of forest. And this can be what we use as an EPA, a typical EPA standard spreadsheet that's available, where you can plug in, if you're doing a CHP analysis for your building or for your business. These are available on the internet through the EPA, and you can plug in and quantify the savings that you would, the environmental savings that you would achieve. As I said before, it's about the size of a compact, about a large office desk, about the size of a sheet of plywood. Typically, they're landed inside a boiler room or outside nearby a boiler room, and the rest of this is pretty simple. Typically, there's no interruption to the operation of a building during the course of installation, with the exception, potentially, of a short electrical shutdown to tie in the electrics. Typically, the plumbing can be done fairly seamlessly, and the rest of it is done without any interruption. The economic advantage of CHP is that it reduces your electric bill. It slows your meter down while it offsets electric costs. It reduces boiler gas consumption because you're using the heat from the cogenerator that otherwise would have been produced by your boiler. It reduces exposure to price volatility because you're very cost effectively producing both electricity and heat simultaneously. It will extend boiler life because your boilers don't have to run as frequently, and will reduce maintenance costs on those boilers for the same reason. Typically, if you have a good location, you can pay this thing off within about 3 to 4 to 5 years. It really depends on what your first costs are and what the cost of energy is that you're paying. This example makes these particular assumptions, that you're paying $1.30 a therm for boiler gas, that you can buy cogen gas at a lower rate of $1 a therm, and that you're paying for your electricity at a 13 cent per kW. That's kind of a blended rate, so because I'm not taking any calculation in for demand reduction in this analysis. The turnkey cost is $4,000 a kW. So for a 75 kW system, it would be about $300,000. The maintenance cost is $1.35 an hour, and you're receiving an incentive from the utility of $50,000. This chart demonstrates the savings and the payback that you get based on run hours, and this really tells the whole story. At 4,000 run hours a year, it's going to take you 8 years to get your money back. At 7,000 run hours a year, you can pay it off in 4.5 years. If you run it 90% of the time, you can pay it off in 4. It's simple math, and it really tells the story. What you need is a consistent base thermal load. A good way to think about combined heat and power as this is a boiler. Oh, by the way, it makes electricity. If you run it based on thermal demand so that the unit is running and producing hot water that you're going to be using on site, this is where you're going to get your best performance. Obviously, electric rates play into it, and that's why combined heat and power is not a cost-effective choice in regions like the Midwest or the Far West, where most of the power that's utilized comes from hydro plants and the rates are very low. Typically, we're looking for a single electric meter that has a large electric use. It's not possible to connect an induction system to multiple electric meters. That's why if you have an apartment building where every apartment is individually metered, you can't tie into the individual metering of the apartment. You have to look at the common meter of the apartment building and determine if that is a candidate or not based on that usage. The hot water provided by the system, we're looking for at least 3,000 therms of hot water a month as a base load use. So if you go back and look at your gas bills for your building and you're saying, wow, I'm burning 5,000 therms in August, I think I might be a candidate for combined heat and power, and I think you might be. For residential buildings, we're looking at clients that are buildings that hold over 200 residents or clients or apartments. And as I said, chilled water is really an option, but it's the heat and the electricity that we're looking at first. When you're sizing a system, you want to size it based on the smaller of either the electric or the thermal load. You don't want to try to tackle the entire load of the building because it's not cost effective to do that. This chart is apologies for the writing in the center, but what this chart demonstrates is a typical annual heating consumption, where you have your peaks of thermal consumption in the wintertime, so that would be on either edge, and then you have a smaller amount of consumption in the summertime, which represents really your domestic hot water load. What we try to do when we size cogeneration is the light purple area down in the bottom. We're trying to base load the thermal energy. We'll let the boilers take care of the peaks. We'll provide a base load, and at the same time, we'll be providing a base load of energy as well. So that's the basic concept. I'm just going to move along here. These are some typical applications. We've talked about most of them: nursing homes, hospital, housing, sports facilities, and so on. Assisted living, hotels, like this one would be a good candidate. And then I want to just touch briefly about the funding opportunity that American DG brings to the table. Instead of you having to make a large capital purchase, the way American DG approaches it is we call it an on-site utility system, where we make the investment. We own and operate the equipment. We allow you to purchase the equipment at any time during the course of the agreement. We agree to sell you the energy that we produce at a prescribed discount below whatever you would have paid in real time for that energy. So if we tell you that we'll give you a 10% discount on heat and electricity and you're paying 10 cents a kilowatt hour for electricity, the energy that we sell to you, we'll bill you at 9 cents a kilowatt hour. If 5 years from now you pay 20 cents a kilowatt hour, we'll sell you that energy at 10% below that, so that's 18 cents. And the same thing goes for the thermal energy as well. So we're able to make our money back by selling you the energy that we produce at a rate below whatever it is that you pay in real time. Of course, we ask you for a fairly long-term agreement for that, but the benefit to you is that your capital is untouched, you improve your cash flow from the day one the system starts up, and you pay nothing at all for the maintenance and operation of the equipment until or if you want to take it on yourself. We call this our on-site utility plan and program, and if you'd like to talk to me about that offline, I'd be glad to share that with you. Again, run hours are the name of the game. So correctly sized, running an adequate number of hours, operated responsibly, not wasting the heat, and reliably maintained, you're going to find that your cogeneration system is going to provide you energy savings year after year after year. These are the blue boxes. They can be installed inside or outside. Here's an outside shot with a couple of them outside a athletic facility. And these are some of the types of facilities that are very good candidates for our type of small package cogeneration. If you have any questions, see me afterwards. I think we'll be taking questions after the other two presenters. Thank you very much for your time.